All right, let's suppose that the weights of cattle, let's identify what we have. The weights of cattle in South Texas are approximately normally distributed. Okay, that's good. So we're dealing with a normal distribution, más o menos. And that the average steer weighs 1,400 pounds with a standard deviation of 120 pounds. That sounds an awful lot like mu in the county, or in this case in the region, South Texas. So mu is 1,400 and sigma is 120. A rancher is willing to go to market if the average weight of his steers is 1,600 pounds. Sounds a little out of whack. So here I see the words average weight, but I know that the average steer weighs 1,400. So this is a classic question. Which one's mu and which one's x bar? Well, mu is the population, and here we say all of South Texas, right? So that's our population. And this guy, his steers, so this is like on the ranch. So just his, this is x bar. X bar is equal to 1,600. And the question then is, what is the probability that the rancher steers are greater than 1,600 pounds? Okay, so what is the probability that the rancher steers, some random variable, is greater than 1,600, right? This is what we're asking. What is the probability? Because if the probability is high, then the rancher can turn around and go to market and he'll probably get what he wants. If the probability is low, then the rancher's probably not going to go to market and not get what he wants. You know, if you've done a couple of these practice problems already, you're probably thinking, well, he's not going to get the money and he's not going to get what he wants. And so that's probably the case. But maybe you don't see that right now, and that's perfectly fine. When in doubt, draw it out. So let's go ahead and draw this out. We know that it's normally distributed, or approximately normally distributed. And we know that mu is somewhere in the middle here, and we know how to build a normal distribution. So let's go ahead and do exactly that. 1,400 is my mu, and I know that every sigma is 120. So here's a sigma, and here's a negative sigma, and so on. Sigma, sigma, negative sigma, negative sigma, and so on. So 1,400 plus 120 is 1,520 is here, 1,640, 1,760, and we can do this in reverse, obviously. 1,280, 1,160, and off on the side is 1,040. So every sigma, I'm adding 120 pounds, this when I go to the right, and on the sigmas on the left, I'm subtracting 120 pounds when I come left. Okay, and that's how I get my sigmas. That's how we build a normal distribution, and that's where we are. So my x, I'm going to denote it in blue here, is 1,600 pounds. Where is 1,600? 1,600 pounds is going to be in here somewhere. Here's my x, it's 1,600. If my average is right down the middle, well, you can tell that, you know, it's going to be kind of difficult here for us to get that because we're kind of away from the mean, but that's just big picture. Let's ask the question again. The probability that x is greater than 1,600 is all the space that's greater than 1,600 going off to the right. So what is the area under the curve that is to the right, greater than, right of 1,600? That's the question. And in order to solve that, we need to bring in our table. So let's bring in our table and let's expand it out. Ta-da! So here we have our standard distribution table, and you see that we're going to have to calculate some sort of z in order to make this calculation, because we know that this is about normally distributed. So in order to calculate z, before we do that, let's go back to our stats over here. Before we do that, one of the things we like to do is we like to convert from our normal distribution, let me do that in white, normal distribution to what we call the standard normal distribution. Our standard normal distribution looks exactly the same as our normal distribution, except the mu, let me get a little more space here. The mu is 0, and instead of having a variable x as our x-axis, we have the variable z as our x-axis, or our z-axis, I suppose, where each sigma is just a standard deviation. 1, 2, 3, -1, -2, -3. All of these numbers are negative. All of these numbers are positive. And we are going to go from this x down to the same position on this point, but this is going to be our z. And in order to make this transformation, in order to transform from our normal distribution to our standard normal distribution, we have to do a z transformation or a z-score, or let's do it up here at the top so that we can keep our, you know what I can do? Since we've gotten fancy with this stuff, I can just cut them out. And let's copy that. Copy. Let's find some black space and paste. Excellent. All right. So in order to do that, we have to do a z transformation. Let's do it in white. Z is equal to x minus mu over sigma, except that this is not a single observation, is it? No, it is a sample mean. How do we know that this is a sample mean? Because we're looking for, where's our question? We're looking for the average weight. Let me do it in blue. We're looking for the average weight of the steers on the ranch. Average weight. All right, so we know we're not looking for the probability of one steer. We're looking for the probability that if we gather all the steers, we'll have some average. Okay, so we're looking for the sample mean here. And if we're looking for the sample mean, then we have to modify our z calculation. It's an x bar. So this needs an x bar on top. And if we do that to the top, we need to divide by the total number of observations at the bottom. And we don't have an n, so let's calculate. Let's just make one up. So let's say that the rancher turns around, and in order to measure and calculate his own x bar, he goes out and weighs, I don't know, 40 steers. Right? He's got, I don't know how many steers. He's got 600 steers on the property, and he can't weigh them all because it's just a hassle. If you've ever worked with cows, it's a real pain. And so he's got enough, time to weigh 40 steers. And so he weighs 40 steers, and that's going to be our N. All right. So this calculation, given our examples, should be then the average, the sample mean, minus the population average, 1,400, divided by sigma, which is 120, divided by the square root of n, which we now know that the rancher measured 40 steers in order to get that calculation. All right, so this converts to 1,600 minus 1,400 is 200. So right away we know this is positive, right? So we're dealing with the right-hand side of mu. It's positive 200. That's great. And in the denominator, through the magic of mathematics, we know that 40 square root is equal to 6.32, and that 120 divided by 6.32 is equal to 18.98. 18.98. If you say 19, it's probably an appropriate approximation. And that 200 divided by 18.98 is equal to 10.5. 10.5. So our z-score is equal to 10.53 actually, which sounds like it is way, way far away from the normal. And let's go ahead and draw this curve one more time. Curve in the middle. Actually, I'm going to make a point here. Curve in the middle. And then we go out. Mu is here, sigma, sigma, sigma. And we know that sigma, you know, if we were to do 10 of these, and we know that 10 is over here somewhere, way out, 10.53. At this point, we need to bring in our z's table. Where's our z table? Here's our z table. At this point, we can look at our z table, and our particular z-score is so large. This is a terrible example. It's so large that it is, you know, 0.999999997, right, is the area left of our curve. So what that tells us is that the space to the left, all of the entire population, is equal to 0.9999999, whatever it is, such that the area under the curve greater than 10.53 is 0.00000, you know, 1 something. I don't know. It's so big. Our z-stat is so big that the area under the curve is almost 0. All right. So should this guy go to market? No. Do not go to market. It is unlikely, super unlikely that this is the case. And you know, as a consultant, you would turn back to your guy, you would turn back to your dude and say, where's our question? Here's our question. You would turn back to your guy and say, hey, look, bro, this expectation of 1600 is so unlikely to happen that either you have a magic ranch or you need to shift your expectations to something that's a little bit more realistic. And I want to talk a little bit about why that number came out so big. When we have a traditional normal distribution, let me do this in white. When you have a traditional normal distribution, and we talk about a single observation, you have a, you know, we have a distribution that looks kind of like this. 1, 2, 3, -1, -2, -3. But when we have a sample distribution, that normal curve actually is a lot taller. And so this curve comes in super tight, and then it grows in the middle, and then it comes back down and grows super tight. What that means is that it's highly unlikely. It's pushed in, right? So you have more in the middle, when you deal with an X bar as opposed to when you deal with a single observation. When you deal with a single observation, we have stuff all over the place. But when we deal with a sample mean, you know, we have these better averages. It is more unlikely that you're going to walk away from the middle because you've already taken an average and brought stuff into the middle. And so while a steer, this is 1400 in the middle, while a, and 1600's over here somewhere, while a steer, while it's not unlikely that you might have a single steer at 1600, it is super unlikely that you would have an average weight of steers at 1600. And that's one of the reasons you might get different results if you compare single observations and follow a very similar example than if you follow sample averages.